Good morning, all. Okay, we'll solve this problem first related to RMS, average, and peak to peak values. Let's try to solve this problem. So already we have done this problem. So the sine wave has a peak value of 25 volt. So peak value is given now. Peak value is given now. Okay. That is Vm. It's already given. Right. Determine the following values: RMS and peak to peak and average value. What is the RMS value? The waveform given is sine wave. For a sine wave already they have evaluated the RMS value. Vrms equal to Vm by root 2. Right. Vrms is equal to Vm by root 2. Okay. Or 0.707 into Vm. Vm is already given 25. Right. So we will get 17.67. And peak to peak value. One peak value is given. Okay. One peak is given as 25 volt. Right. What will be the value of peak to peak? Peak to peak means from here to again here. Here what you will get? Minus 25. So peak to peak we will get 50 volt. Right. And average value for the sine wave. It's already evaluated in the previous class. 2Vm by 5. 2Vm by 5 are 0.637 into Vm. So if you substitute Vm value, we'll get 15.9. Right. This the period of a sine wave is 20 milliseconds. We have already solved this problem yesterday. And the frequency of a sine wave is 30 hertz. What is the period? Okay. So T is equal to 1 by F. So 1 by 30 you will get 33.3 millisecond from here. We can see time period is given, frequency you have to evaluate in the first problem. Frequency is given, you have to evaluate the time period in the second problem. Okay, we'll start with the other concepts. What is reactance, impedance, susceptance, and admittance? Okay. Actually, what is reactance? First, we'll discuss. Reactance is the opposition of any circuit to an AC signal due to the elements inductance or capacitance. What is resistance? Resistance. You can answer that. What is resistance? The opposition offered to the current flow because of the resistive element. Okay, because of the resistive element. Here, because of the inductive or capacitive element, opposition will be offered to the flow of AC current here. So that we are calling it as a reactance. Right? And it's represented with the symbol X, whereas we will represent the resistance with the R. Okay. And if it is a reactance offered by the inductor, okay, we are calling it as the inductive reactance. Inductive reactance. And if it is a reactance offered by the capacitor, we are calling it as a capacitive reactance. Capacitive reactance, and we are representing it with the XC. Reactance offered by capacitor. Here it is offered by the inductor.
Sir, explain once again, sir.
Okay. Simple amount. Resistance and TD. What is the resistance?
Which opposes the flow of electrons.
Flow of current. Okay. And that is offered by the resistive element there. That we are calling it as the resistance. Okay. And remaining elements, inductance, capacitance also opposes the flow of electrons. That is nothing but resistance only. But the opposition offered by the inductive or capacitive elements, we are calling it as a reactance. Okay. And if it is offered by the inductive element, we are calling it as an inductive reactance. If it is offered by the capacitance, we are calling it as a capacitive reactance. Okay. And the impedance. Okay. The impedance is defined as the ratio of. Okay, thank you. The impedance is defined as the ratio of sinusoidal voltage to the sinusoidal current. It is also defined as the total opposition offered to the flow of sinusoidal current. Here we are representing this with the Z, What is resistance? R is equal to V by I. That is in case of the DC circuit. Okay, that is in case of DC circuit. In AC circuit, same resistance, we're calling it as the impedance now. And that is a ratio of V by I. Here, for the AC quantities now, for the AC, this voltage might be AC voltage and current might be AC current. So this ratio we are calling it as a impedance. Uh, we have one more definition. Impedance is the opposition offered for the AC current by resistive element and as well as the inductive or capacitive elements. Inductive or capacitive elements. That is another definition for impedance. So impedance means we will add all oppositions that caused by the resistive elements and the inductive or capacitive elements. So we're calling it as the impedance. Okay. And the real part of the impedance is resistance and the imaginary part is reactance. So we are representing with Z is equal to R plus J into X. R plus J into X. This is the opposition offered by resistance. This is opposition offered by inductive or capacitive element. Okay. So this is the representation for Z. And this R we are representing on the x-axis R, and J means it will be rotated with the 90 degrees angle. It will be separated with the 90 degrees angle. This X, J operator, if you're placing J operator means it will be rotated with the 90 degrees angle here. And the resultant here we are getting as a Z. The resultant we are getting as a Z here. You can see here. See from this figure, this is the real part of the impedance. Okay, real part of the impedance. This is the imaginary part of the impedance, and this is the resultant. Okay, and how to find the magnitude of the impedance here? One is real part, another one is the imaginary part. So we'll take square root of r square plus x square, r square plus x square here, and for these vectors we will get hello. Yes. For these vector, we will get an angle also here. We will get an angle. Magnitude we will get in a polar or a vector form. We will get the magnitude and we will get some angle also. This is the representation for AC quantity in polar or vector form. Magnitude. This is the way to find the magnitude. Okay. If there is R plus the X we are having. So for this is the magnitude and angle. How to find the angle here? Magnitude of J into theta here. Okay. Theta is equal to tan inverse of x by r. Tan inverse of x by r here. Okay. And for inductance, we will take plus z here. For inductance, we will take plus z. And for capacitance, we will take minus z. Means we will get r here, z here, minus z, right? And here we will get the z. This is minus j. Representation of z. So here, with respect to the x-axis, here also we'll get the angle theta, and that is theta is equal to tan inverse of here. In case of capacitance, so this is the impedance formula. Okay, R minus J into XC. In case of inductance, R plus J into XL. This is the angle tan inverse of xc by r. Okay, this is the magnitude, this is the angle in case of the capacitance. Is it clear? First, what is the reactance? What is the reactance? You can answer now.
It's also like an resistance.
Yes, it's also like a resistance, but it's offered by the
Inductance or
capacitance. Very good. What is impedance? What
no,
is
sir. I did not got it.
Voltage
Explain
by
it.
current, sir.
voltage by current? Voltage by current, we are calling it as resistance, na?
AC circuit, sir.
In DC circuit. Okay, that is resistance.
Impedance means sum of all the opposition current oppositions, sir.
In AC circuits, you can say it as the ratio of sinusoidal voltage to current, or else it is the opposition offered by this. It is the opposition offered by resistive elements as well as the inductive or capacitive elements. Okay, so what is the formula? We are representing with Z, and AC quantities we will represent in vector or polar form. So this is a representation in polar form. Okay, for AC quantity it will be having magnitude and angle also. So for any complex wave, so this is a formula to find the magnitude, right? And this is the formula for finding the angle, tan inverse of imaginary part by real part. Okay. So what is the admittance now? What is the admittance? The concept of reactance we discussed, impedance we discussed, and we will discuss the susceptance and admittance now. Susceptance and admittance. Actually, in parallel circuits, the inverse of the parameters will be useful. Okay. In parallel circuits, the inverse of the parameters will be useful here. The inverse of impedance. See here, the inverse of impedance, we are calling it as the admittance. So that we are representing with y. So y is equal to 1 by z here. What is z? Z is equal to r plus j into x. Na? So y is equal to 1 by r plus j into x. So we will get again one real part and one imaginary part here. Real part and imaginary part here. This real part we are representing here with the G. Okay. And imaginary part we are representing with the B here. So the inverse of impedance is admittance, and it is the defined as ratio of sinusoidal current to voltage. What is the name for G? It's, we are calling it as a conductance. Conductance. Okay. and the imaginary part we are calling it as the susceptance. Susceptance. Okay. So z is equal to r plus j into x, but y is equal to 1 by z. This we are calling it as impedance. This is admittance, and here also we will get one real part and imaginary part. Real part we are representing with the G, and it's named as the conductance. And imaginary part is represented with the B. We are calling it as the susceptance now. So what is G? G. It is the inverse of R, 1 by R. Okay, conductance is the inverse of the resistance. Okay, susceptance is the inverse for reactance. Reactance and susceptance. Resistance and conductance.
Sir, is that XL or XC, sir?
No, just X. If it is offered by inductive, then we will take L, or else we will take C. Okay, this is a common concept. Just reactance I'm explaining. Reactance, susceptance, inverse is susceptance, resistance, inverse is conductance now. Here, in DC circuit, the opposition to flow of current is only the resistance. Okay, only the resistance. But in case of AC circuit, it is because of resistance and inductance and capacitance. So because of the three elements, we are getting the opposition in case of the AC circuits, and that we are calling it as the reactance. Here, this is the formula for inductive reactance. XL is equal to, we are writing it as omega L, and XC is equal to 1 by omega C. This is inductive reactance is equal to omega into L. Capacitive reactance is equal to 1 by omega C. We can write it as omega is equal to 2 pi F into L, capacitance 1 by 2 pi F into C here. Okay, 1 by 2 pi F into C here. And this is the concept of three-phase alternating current, three-phase AC waveform. Okay. Initially, we are representing. We will be having three phases: R, Y, B. Okay. And those phases will be displaced with the 120 degrees angle here. 120 degrees angle here. R phase is displaced with Y with 120 degrees angle, and B is displaced again, means lagged with the Y by 120 degrees angle. Okay, so this is the representation of the three-phase waveform here. Here Vm sin omega t. Okay. In y phase, the magnitude will be same, but the angle is displaced with the 120 degrees angle here. And in B phase, it's displaced by 240 again. See, let us suppose this is phase 1, that is R phase, and Y phase, and B phase. This R is starting at 0 here, at the reference it is starting. And B phase, it's starting at after 120 degrees angle. It's 90 plus 30, it's 120, okay? 120 degrees angle. And B phase is starting after 120 again, after 120. Since from the reference, it is starting at 240 degrees angle now. 240 degrees angle, okay? Now this 240, you can write it as plus 120 also. That is 360 minus 120. So Vm sin omega t, Vm sin omega t minus 120, Vm sin omega t plus 120 you can take, or minus 240. Just I will show you how to calculate the RMS value. So for a half wave rectifier here, this is half wave rectifier. Half wave means there is no negative waveform, okay? For the complete cycle, output will be only during the positive half you are getting the output. Negative you are not getting. So what is the RMS value? Oh, sorry, it is how to calculate the average value. 0 to the duration you will take from 0 to pi here. 0 to pi here. And the waveform will be Im. Waveform will be I is equal to, for the current waveform we are calculating, I is equal to Im sin theta into dt by, but the total duration here, what is the time period here? Time period is 0 to 2 pi. Total time period is 2 pi, but we are having the waveform from 0 to pi only. So in the down we are writing the time period here, okay? But waveform is present for 0 to pi only, 0 to pi only. So substitute the values, we will get Im by phi for the half wave rectifier, okay? This is the calculation form factor for the half wave rectifier. is the RMS value. RMS value will be different for sinusoidal waveform and for remaining waveforms also. It will not be fixed. Im by root we have taken RMS value for AC, but here for the half wave rectifier we will get Im by 2. Average value already is calculated in the previous slide, so we'll get 1.57. I will share these slides. Okay, so this is a vectorial representation of these waveforms. Okay, so at this angle this will be the magnitude. Just if you integrate this here, this is the magnitude M we are representing here, M. Okay, and the angle we will get here, means it will be displaced. We are starting from 0. Okay, we are starting from 0. At 0 magnitude is 0, no? It's 0. Now we have moved to some 30 degrees angle, okay, then the magnitude will be here, and we have moved to 90 degrees angle, here, and the magnitude will be here. Okay, so in this way a sinusoidal waveform can be represented as a vectorial or polar form, and we can represent many AC waveforms on a single vectorial picture here, vectorial or polar picture here. This we are considering as a reference. Okay, this has started at 0. This has started at 0. With reference to 0 here, alpha is displaced. This waveform 1 is in leading here. 1 is in leading with an angle of alpha, here. So this will be the magnitude Em, and this is the angle here. And for the same waveform, what is the magnitude here? Im. Okay, this is a current waveform, this is a voltage waveform. Current is in lagging now. Current is lagged by an angle of alpha here. So after alpha angle, this waveform 2 has started. After alpha angle, waveform 2 has started, and this magnitude is Im here. It's less compared to Vm. It's less compared to Vm here. So this is on a single polar or vectorial background, we can show the many AC quantities. Okay, and this is the addition or subtraction of the waveforms here. We can do addition and subtraction of the waveforms here. Magnitude and the angles we will take here. It's not required. Just we are considering a voltage waveform V is equal to Vm sin omega t. Okay, if AC voltage is given to the resistor, then what happens? We will see here. V is equal to Vm sin omega t. Okay, AC waveform. It is given as an excitation for the resistor here. It's given as a excitation. Okay, now what will be the current here? I is equal to V by R, right? I from Ohm's law, I is equal to V by R. Vm sin omega t by R. Voltage waveform is Vm sin omega t. If only DC is given, we won't get this term. Only V by R will take. But because of the AC quantity, we are getting the sin term here, right? We are getting the sin term here. And what is the magnitude here? Im is equal to, this is the magnitude, right? This is magnitude and here angle is 0. Angle is 0 here. And here voltage waveform has been considered. Okay. And current waveform has been considered. If you take B is equal to Vm sin omega t, that is the voltage waveform. Here I is equal to Im. This magnitude we are representing with Im. What will be the angle? There is no change in angle. Sin omega t we are getting directly. So there is no angular difference here. No angular difference between these two waveforms. So here both the waveforms are starting at reference only here. Both the waveforms are starting at reference only. So the angle is same, but the magnitude is different. What is the magnitude? I is equal to some V by R. So we are getting the less value for the current. Okay. So this is the representation here. Angles will be starting and ending at the same point, but the magnitude will be different. Voltage is higher, but the current is lower here. Okay. So when AC supply is given to a resistor, there is voltage and current are, we are calling it as are in phase. In phase. Both are in phase. Okay. There is no phase difference here. And when an AC supply is given to an inductor, then what happens? What is the voltage across inductor? Already we know. So whenever AC voltage is applied to a purely inductive coil, okay, the EMF is produced due to self-inductance. We already discussed this in the basic concept while explaining the L inductor or inductance in the initial classes. When an AC supply is given to an inductor, okay, some back EMF is produced because of the self-inductance, and that EMF we are representing with V is equal to L into di by theta. This is the voltage equation. No? This is the supply. Okay, V is equal to L into di by theta. dt. Sorry. What is the supply voltage here? V is equal to Vm sin omega t. L into di by dt. Okay. From this we will get the I. What is the current flowing through inductor? How to get this? Voltage equation at the inductor is V is equal to L into di by dt. This is the supply. V is equal to Vm sin omega t was given as an excitation here. Substitute here. So what is dA here? Vm sin omega t into dt by L. Here we are getting 1 by L. So integrate this, right? Integrate this, we are getting I. That I is equal to Vm by L into integral of sin omega t. Integral of sin omega t. What is the integral of sin omega t? Minus cos omega t we are getting here. Minus cos omega t. Or we can write it as this is the given voltage waveform. The current we are getting this one minus I is equal to Im minus cos omega t. So instead of minus cos, we can write sin omega t minus pi by 2. Sin omega t minus pi by 2. So If we are representing here, if it is voltage waveform, it's starting at 0. This is Vm. Now, where the current waveform will be starting here for a pure inductor after 90 degrees of angle. It is lagged, okay? Minus pi by 2 means it is lagging with respect to Vm here, and the magnitude will be less. So this will be the current waveform Im. So just remember that for a pure inductive coil, if an AC voltage is given, the current waveform is lagging by 90 degrees here, by 90 degrees here. Okay. And what happens if the same AC supply is given to a capacitor? I will show the derivations here. Okay. Again, from the basic concept, capacitor we discussed now, I is equal to C into dV by dt. Okay. I is equal to C into dV by dt. Now, this V is given as an input here. So we will substitute here C into d by dt of Vm sin omega t. So at the end we will get Im is equal to Im sin omega t plus pi by 2 we will get here. Plus pi by 2 means it's leading compared to, this is the voltage waveform. It's starting at 0. It's starting at 0. The current magnitude will be less. Magnitude will be less, but it's starting at 90 degrees leading here. It is starting here. 5 by 2. Okay. This is 5 by 2. So the current is in leading compared to voltage here in case of capacitor. I will show you these derivations. So when pure resistor V is equal to Vm sin omega t is excitation here. Okay. This is the input. This is the input, and output we are getting I is equal to V by R. I is equal to V by R. So there is no angle difference. We are getting both the waveforms are starting at 0 here. Okay. But in case of inductance, the same voltage V is given as an input. But what is the voltage across the inductor? Voltage across the inductor. This is voltage across the inductor, right? already we discussed in the first unit itself. When I explained inductance and capacitance concept, we discussed this voltage equation, right? V is equal to L into di by dt. And one more question. If a DC supply is given to inductor, then what happens? If a DC supply is given to inductor, what happens? Any answer? What happens? This di by dt becomes 0. Why? Because for a DC supply, it will be constant. No? So this derivative, there is no change. So we are getting 0. Voltage across any element is 0. Then it is acting as a short circuit or open circuit.